Faraday's Law 1. In words, Faraday's law is the EMF induced at the perimeter of any loop is equal to the negative rate of change of magnetic flux with respect to time. The negative rate of change of magnetic flux with respect to time. That doesn't have a lot of meaning right now, but very soon, within a few videos, hopefully it will. The single loop equation for Faraday's law goes something like this. There's an EMF, and it's equal to the negative rate of change of the magnetic flux with respect to time. If we have multiple loops, let's say we have our coil of wire and then we've got lots of loops and they're stacked closely on top of one another, then it's the same equation except we've got a factor of n in there, kind of like that. We have a coil and we have a magnet and we wish to induce an EMF and a current if the coil is a conductor. What type of motion must there be between the coil and the magnet? Well, there has to be relative motion. If you tape the coil and the magnet together and just wave them around, there won't be an induced EMF. We have to have relative motion between the two. Now, what are a few ways that we could accomplish inducing an EMF in a loop? Well, if we want to change the magnetic flux, here are a couple things we could do. We could change the strength of the B field, make it stronger, make it weaker. We could increase or decrease the size of the loop, because you remember that magnetic flux is a measure of how many magnetic field lines are poking through a window of a certain size. And if we change the strength of the B field, that will change the flux. If we change the size of the window or the loop, that will change the flux. And if we rotate the loop, in effect, doesn't that change the size of the window also? Any of those will cause a change in magnetic flux. Sometimes in demonstrations, we show this induction and we use an instrument that has a needle attached to a coiled spring and a loop of wire, and it can measure very tiny magnitudes of induced currents, and that's called a galvanometer. You might see one in class sometime. But the EMF induced in Faraday's law is induced because there's an electric field that's induced. And the induced EMF is a consequence of that induced electric field. More on this later. So a more complete Faraday's law equation for one loop actually has two equal signs. A more complete equation might look something like this. And again, this is assuming we just have one loop. That's the part that we've met already. We could also say, you know what? We could do the dot product of the induced electric field around the loop with each little perimeter segment, if you will. There's a more complete form of Faraday's law, and we can use any two of these bits if we want in order to figure out some answers to problems related to Faraday's law. Let's summarize what we've gone through here, because the first time you hear some of this stuff, it's a little bit strange. Let's take any area with a real boundary or an imaginary boundary, doesn't matter. Whenever the magnetic flux, which is symbolized by sub B, whenever the magnetic flux is changing within that area, and we said there were a couple ways to do that. You can change the strength of the magnetic field, you can change the size of the loop, you can rotate the loop. All of those will change the magnetic flux. Whenever the flux is changing, then there is an electric field that is created or brought into being at the edges of that boundary, which means there is also an EMF or voltage created or brought into being at the boundary's edges. If the boundary is real, in other words, if there's actually material there at the boundary, And if it's a conductor, then the EMF created will induce an electric current. The greater the time rate of change of magnetic flux, the stronger the electric field and the stronger the EMF that are generated.